Hi everyone. So today we're going to be working on solving trigonometric equations like we were last week, but we're going to be getting into using some slightly different methods. So we're going to get into solving equations where we have to start by factoring and then kind of move on to the methods that we talked about last week. So just to kind of give a heads up for what this week is going to be like. So we'll continue to talk about solving different type of trig equations in tomorrow's video. And then that's actually going to be it for trigonometry. So after tomorrow's video, we're going to be moving into some other topics, and some of them will be related to trigonometry, but it won't be like directly about trig. So, congratulations, we're almost through this part of the course. But yeah, so let's get into some examples. So today's basically just going to be a bunch of different examples that will bring up different types of ideas. Okay, so let's start with an example. So, and in this video, by the way, we're going to be focusing on solving these equations just for solutions between 0 and 2 pi, just for simplicity, because the equations we're getting into are a little bit more complicated. Just to make it more simple, let's just stick with solving from 0 to 2 pi. But I will say that if you wanted to provide all solutions, it would be very, very similar to what we were doing last week. So basically just adding on 2 pi or 2 pi k to your solutions. So we're going to find all solutions to move this 2 cosine squared of x minus cosine of x minus 1 is equal to 0. And we're going to be focusing on, like I said, on the interval where x is going to be between 0 and 2 pi. Okay, so what is different about this equation compared to some other equations that we have been working with? Well, we have been solving things like, let's say that this cosine of x wasn't there and it was just 2 times cosine squared of x minus 1 equals 0. We did actually solve stuff that looked like that last week at the beginning of the week. And then if this cosine squared wasn't there, well, we know how to solve something that looks like this, right? That's something that we were also solving last week. So when you have both of these things together, that's what tells you that you want to factor. And so I want to kind of rewrite this equation just using a little bit of color and writing it a slightly different way to help you kind of see how this is going to factor. So another way of writing cosine squared of x is saying cosine of x squared, right? So I'm just going to rewrite this as 2 times cosine of x squared minus cosine of x minus 1 is equal to 0. So notice that this is of the form where you have something squared, and then you have just that thing without it being squared, and then you have a number. So this kind of looks like things that we would have factored, back in 141, right? This looks like a quadratic equation that you can solve by factoring. So what we're going to do is we're going to, instead of writing cosine of x, we're actually going to replace that with a different letter that will help us kind of see how to factor this. So what we're going to do is we're going to use the letter u. It's like for some reason the letter u is just very commonly used for this type of thing. You'll see that especially in calculus 2. So we're going to let u equal cosine of x. So basically what I mean by that is we're going to rewrite our equation, and everywhere where we see cosine of x, we're going to replace it with the letter u. So we would get 2 times u squared, and actually meant to make this in black. So that's really just the cosine of x part that we're putting in purple, minus u minus 1 is equal to 0. So what we're going to do is we're going to focus instead on solving this equation just because it kind of looks easier, right? It looks like something that you would know how to factor. And then once we have our factorization kind of set up, or once we get our kind of general solutions, then we're going to go back to rewriting it in terms of cosine. And I think after you do some practice with this, you might not actually have to do this step. You might be able to see how to factor it without doing this kind of U thing. But I think it's helpful at first just to really kind of get a sense of the pattern. Okay, so how do you factor something that looks like this? Well, in general, I always like to suggest using trial and error for factoring simple things. There are, like, you might have learned something called the AC method, or you might have something you do with like a box or a diamond. There's all sorts of different methods. What I generally like to suggest is when you're factoring, so we know that we're going to put something here and something here, right? Those two things need to multiply to give us 2u squared. And so the only real possibilities that would work for that would be 2 times u and u, right? Those are the only two, at least, whole numbers that we can use that would give us a 2u squared. And then we have to figure out which two numbers to put here and here, and we know that those two numbers have to multiply to give you -1. And so that means that we're going to have a +1 and a -1. And it's, like I said, trial and error. Try one, see if it works. If it doesn't, then switch it. So maybe let's try -1 here and +1 and see what we would get if we tried to multiply this out. So if we multiplied this out, we would get 2u squared plus 2u. So 2u squared plus 2u minus u minus 1. And so that would be 2u squared plus u minus 1. And notice that's not what we wanted. We wanted a minus u and we got a plus u. And so that tells us, okay, our trial and error was the wrong trial. It was an error. So that's fine. That means that we're going to go back and we're going to try it the other way. So instead of saying minus and plus this way, let's switch it. So we'll have a plus here and a minus here. And if you multiply this one together, it will work, because you would get 2u squared minus 2u plus u minus 1. And so that would give you 2u squared minus u minus 1. And that matches with what we had. So now we have the correct factorization. Okay, so when you're solving something by factoring, that means that you have two factors in this case, and you're multiplying them together and you're getting 0. That tells you that one of those two things equals 0. So we either have 2u plus 1 is equal to 0, or we have u minus 1 is equal to 0. And so, and by the way, at kind of any point that you want to, you can put back in the cosine of x. So I'm going to wait until we've solved these for u. But if you wanted to, after factoring, you could put cosine of x back here and here, right? You could rewrite this as cosine of x and this as cosine of x, and then solve from each step. Or you could here write 2 times cosine of x plus 1. It doesn't matter. Like, u is just kind of a stand-in to make our equation look simpler. So if we were to solve this one, we would get 2 times u is equal to -1. And so that tells us that u is equal to -1/2. And then on the other equation, we would get u is equal to 1. Okay, so now that we've really done all the solving, now we can go back in and put cosine in and see what that tells us, because we're not trying to figure out what u has to be, we're trying to figure out what x has to be, right? That's our original variable. So let me just put this off to the side. So this equation becomes now cosine of x is equal to -1/2. And the second equation becomes cosine of x is equal to 1. So again, if you don't like this u business, if it confuses you, then you don't need to do it. The whole point, though, is that we're basically taking our original equation and we're factoring it as a quadratic. And the reason we did the u thing was because it kind of makes it easier to see what that quadratic is. And then we kind of carried that through all the way with solving, but then we have to go back to our original, what we were actually trying to solve for if we're going to find our actual solutions here. So once we're at this step, now it's just like the problems that we were doing earlier last week. So these are going to be equations that we can actually solve without using a calculator. So for the first one, to solve this first one, we're looking for angles where the x-coordinate is -1/2. So let's look at the unit circle and try to figure out what those angles would have to be. So if cosine of x is -1/2, so that means we could have an angle like this, right? So this would be an angle where the x-coordinate is -1/2 and the y-coordinate is square root of 3/2. So this angle here would be 2 pi over 3. But then we would have another angle that also has an x-coordinate of -1/2, and that would be this angle over here. So this would be -1/2 negative square root of 3/2. And we want to measure this angle this way because we're looking for solutions specifically between 0 and 2 pi. So if you measure this angle this way, so we would have 2 pi over 3, 3 pi over 3, 4 pi over 3. So this angle here is 4 pi over 3. And so that tells us that our solutions are x is equal to 2 pi over 3, and also x is equal to 4 pi over 3. So those are two solutions to our original equation. But that's not the only thing we have to solve. We also have to solve this part, cosine of x is equal to 1. And so for that, we're looking for an angle where the x-coordinate on the unit circle is equal to 1. So where is that going to happen? Well, we're looking for angles between 0 and 2 pi, so it's going to be the angle 0. And so why do I say 0 and not 2 pi? Basically because we're solving it. Notice how I wrote this inequality. Because 0 and 2 pi are coterminal, we don't want to include both of them because we're really trying to find answers that are not coterminal with each other. And so because there's a less than, not less than or equal to sign, if one of your solutions is the angle 0, you want to put 0 and not 2 pi. So another solution we have is x is equal to 0. And so those are the three solutions to this equation. We have x is equal to 2 pi over 3, x is equal to 4 pi over 3, and x is equal to 0. So let me just show you how you could kind of interpret this solution on a graph. So I want to be really clear. On all of the examples we do on this, I'm going to show you what the graph looks like and how you could theoretically solve by graphing. However, I would really, really recommend that when you do these, you don't solve by graphing because I would expect that on a test or a quiz that you could fully show your work and go through this process of factoring. And I would consider if you're just doing it by graphing on Desmos on a test or quiz, I would consider that cheating. And I would need to see all these steps of work. But I do think it's kind of interesting. So how could you solve something like this by graphing? Well, if we take this left-hand side, 2 times cosine squared of x minus cosine of x minus 1, if we write that as a function and say f of x is equal to, or y is equal to 2 times cosine squared of x minus cosine of x minus 1, and we graph that, if we look at where is it equal to 0, that's going to tell us the solutions. And so I just wanted to look at these because I think their graphs are actually kind of interesting. So this is the graph of 2 times cosine squared of x minus cosine of x minus 1. So notice it kind of might remind you of sine and cosine graphs, but it's a little funny. Some extra, lack of symmetry is happening basically. But let's look at our solutions. So the solutions are going to be the places where the graph crosses the x-axis, right? Because those are the places where the function equals 0. And so we see one x value happening at 0. We have 2 pi over 3. We have 4 pi over 3. And then we have another solution at 2 pi, but remember we're not including 2 pi. We're just going from 0 to 2 pi, not including 2 pi. And so those are the three same solutions that we found. And then we can see that if you were asked to find all solutions, well, if you were to add 2 pi to each of the solutions that we got, then you would get 2 pi and 8 pi over 3, 10 pi over 3, etc. So just like with other trig functions, this one continues and repeats its values. Okay, so let's do another example similar to the one that we just did. So again, we're going to have to use factoring. So we're going to find all solutions. And this one's going to bring up something a little bit different that didn't come up in the other one. So sine squared of x minus sine of x minus 2 is equal to 0, and we're finding the solutions on the interval where x is between 0 and 2 pi. Okay, so just like we did with the other one, let's start by rewriting this so that we have sine of x, we're gonna rewrite that, or sine squared of x, we're gonna rewrite it as sine of x squared, just to really emphasize the kind of format of this equation. So the format of this equation is that we have sine of x squared, so something squared, minus that same item, minus a number is equal to 0. And so again, in order to kind of more easily see what it is that we're trying to factor here, we can write the letter u instead of sine of x, and that will help us factor it more easily. So if we rewrite this with a u instead of with a sine of x, we would have u squared minus u minus 2 is equal to 0. So how does this one factor? Well, this one's a little bit easier than the other one because the first thing is just a u squared, there's no other coefficient there. So this one is going to be u and u. And we need to get a negative 2 for our final term. So that means that we have we have like a +1 and a negative 2. And it actually isn't going to matter what we put where, right? Because it's kind of symmetric. So if you were to multiply this back together, you'd get u squared minus 2u plus u. So that would give you the negative u that you want, and then minus 2. So this tells us that either u plus 1 is equal to 0, or u minus 2 is equal to 0. So the first part would say u is equal to negative 1. And the second part would say u is equal to 2. So now we have to go back and put in what our original function was, which was sine of x. So we want to rewrite this as now sine of x is equal to negative 1. And sine of x is equal to 2. And we're looking for solutions specifically between 0 and 2 pi. So let's start with sine of x is equal to negative 1. So that means that we're looking for angles between 0 and 2 pi with a y-coordinate of negative 1. So the only angle that's actually going to happen at is an angle of 3 pi over 2. So because we're only looking for answers between 0 and 2 pi, our only answer coming from that part is 3 pi over 2. So what about this other part? Well, sine of x is equal to 2. That has no solutions, right? Because there's no point that you can find on the unit circle where there is a y-coordinate of 2. It's impossible to ever have sine of x or cosine of x equal to 2, or any number bigger than 1 for that matter. And so this part has no solution. And that doesn't mean that like all of a sudden the whole question has no solution. It basically means that this is the part where the solution came from. So we still have a solution, it's just that the second part did not contribute any solutions. So similarly to the last one, let's look at what the graph of this one looks like. So our original function would be sine squared of x minus sine of x minus 2. So if we graph that function, it looks like this. So again, like maybe let me make this bolder. So let's compare that with the first one. So they both kind of have like interesting different waves going on, but a little different between the two as well. So notice that if we're looking for places where this function is equal to 0 between 0 and 2 pi, the only place where it actually hits the x-axis is at 3 pi over 2. And that agrees with what we found. Okay, so we're going to move on to some examples now that are factoring in a slightly different sense. I just want to say one more time about these types of problems. If you want, you don't need to do this whole u thing. So maybe let me just quickly write down what that would look like. If you wanted to skip writing down, let u equal to sine of x, if you could recognize how to factor that, you could feel free to jump straight to something like this. So if you looked at your equation and you're like, oh, okay, I kind of can see how that's going to factor, you could just jump straight to writing it as sine of x plus 1 times sine of x minus 2. Right? If you were to take sine of x plus 1 times sine of x minus 2 and multiply them together, you would get sine squared of x, which is what we have at the beginning. Then you would get minus 2 times sine of x. You would get plus 1 times sine of x. So together, that would give you this negative sine of x. And then you would get plus 1 times negative 2, and that's where this negative 2 comes from. So if you want, you don't need to bother with the whole u thing, but I think for some people, maybe that just makes it feel simpler in terms of actually doing the factoring. Okay, so let's look at some more examples. So these next examples are still going to involve factoring, but it's just going to be a little bit different kind of type of factoring. So again, we're just going to focus on finding all solutions from 0 to 2 pi for these. So we're going to start with this one. To sine, actually, let's do this one. 2 times sine of x times cosine of x plus 2 times sine of x, or sorry, this was supposed to be a square root of 3, plus square root of 3 times sine of x is equal to 0. And sorry, I forgot to say, on the interval, zero is less than or equal to x is less than 2 pi. Okay, so once again, we're going to be factoring here, but it's not a quadratic the way the other one was. So in this case, we want to focus instead on what are the common factors that we can factor out from both parts of this. So if we have 2 times sine of x times cosine of x plus square root of 3 times sine of x is equal to 0. Notice that both of these things here have a common factor of sine of x. And so what that tells us is that we can factor out a sine of x. So in general, like anytime you're solving an equation equal to 0, and this is going to come up actually a lot in calculus. There's going to be a lot of situations where you'll have different types of equations set equal to 0 and you have to solve them. And one of the first things that you should always think of doing is factoring if you have an equation equal to 0. And so looking for common factors is going to be a really important thing to kind of keep in mind in calculus. So we can factor out a sine of x from both of these. And let's see what we're left with. So if you factor out sine of x, for the first part, you're left with 2 times cosine of x. And then for the second part, you're just left with square root of 3. So now, just like in the previous question, if you have two things being multiplied together equal to 0, that means that one of those two things has to be 0. So from here, we have two options. We either have sine of x is equal to 0, or we have 2 times cosine of x plus square root of 3 is equal to 0. And so from here, this is just like the same kind of equations we were solving early last week. So for example, for sine of x is equal to 0, for this we're looking for an angle where the y-coordinate is 0. So where is that going to happen? Well, one angle where that will happen is at 0, right? If you go to an angle of 0, you have a y-coordinate of 0. So one possible solution to this equation is x is equal to 0. Where else do we have an angle that fits this description? Well, if we go to an angle of pi, that is also going to satisfy having a y-coordinate of 0. And so our other solution is x is equal to pi. So what about this next part? Well, for this one, there's a little bit more that we have to do. So we don't yet have the cosine part isolated, so we want to do that. So we have 2 times cosine of x is equal to negative square root of 3. And then if we divide both sides by 2, we get cosine of x is equal to negative square root of 3 over 2. So we're going to be looking for angles where the x-coordinate is negative square root of 3 over 2. So one angle where that would happen would be an angle like this, right? So this would be negative square root of 3 over 2, 1/2. And so this here is an angle of 5 pi over 6. So one answer from this part is x is equal to 5 pi over 6. We have another angle that fits that same description, which is this angle here, right? This would be another angle where the x coordinate is negative square root of 3 over 2. And so this angle here is 7 pi over 6. Sorry, this is getting a little cluttered. So that would be our other answer. And so taken together, these 4 answers are all solutions to this first equation we started with. So again, let's check out the graph of this thing. So if we were to graph y is equal to 2 times sine of x times cosine of x plus square root of 3 times sine of x, it would look like this. So again, getting these different types of waves. And this one, it's like pretty flat near the x-axis, but we can see that it goes through the x-axis at 5 pi over 6, at pi. Oh, and I forgot 0. We had that one as well. And also at 7 pi over 6. I lost all of them, but those agree with the solutions that we found. And then we see 2 pi again, and just like with the other ones, we'll see that because the shape of the graph keeps repeating, if you wanted to find all solutions, you could just say plus 2 pi k for each of your solutions. All right, so one more kind of along these lines, and then we'll look at a couple that bring in some non-trig equations together with trig equations. Okay, so in this one, we're going to find all solutions to sine of x times cosine of x is equal to cosine of x, and we're going to be solving this on the interval from 0 to 2 pi. Okay, so I want to start with how you should not approach this question. So this would be wrong. So if you decided to solve this by saying sine of x times cosine of x is equal to cosine of x, so you might say, well, I see that I have a common factor of cosine of x on both sides, so I can just divide both sides by cosine of x. So if you did that, you would just get sine of x is equal to 1. And so the only answer you would get out of this, the only place where sine of x is equal to 1 would be x is equal to pi over 2. And that is, we'll see, actually one of the answers. But if you do the question this way, you basically end up losing solutions. So it's kind of like, just to kind of give an analogy, if you were solving something like x squared is equal to 5x. If you were to divide both sides by x, you would just end up with x is equal to 5. But that's not the only solution to this equation. So the correct way to do this equation would be to subtract 5x from both sides. Because then you can factor out x. And from there you can see that there's actually 2 solutions. X is equal to 0 and x is equal to 5. And so similarly here, we're going to want to start by actually subtracting over that cosine of x and doing factoring instead. And really the reason that dividing is wrong, so maybe let's go back again to this example because I think it's a little easier to see what's going on in this example. Why is it wrong to divide both sides by x? Well, because when you divide by a number, you're kind of, without saying it, you're assuming that number is not 0, right? Because you can't divide by 0. So if you divide both sides by x, you're making the assumption that x is not 0. And so what ends up happening is you totally miss out on this solution, which says that actually x could be 0, right? If x is 0, then you would have 0 squared is equal to 0, and that is true. So 0 is a solution. And so similarly here, if you're dividing both sides by cosine of x, then you're assuming that cosine of x is not 0, and that's going to make you lose a solution. So don't do it that way, and now we'll talk about how you actually will do it. So let me just move this down a little bit. So we're going to start by, like I said, let me just rewrite down the question actually, so we have it here. So sine of x times cosine of x is equal to cosine of x. We're going to start by subtracting cosine of x from both sides. because now we can see what we can factor out from each of these. So what do these have in common? Well, they both have a common factor of cosine of x. So we're left with sine of x minus 1. So this gives us now two possibilities. Either cosine of x is equal to 0. So that's the part that we kind of ignored if we divided both sides by cosine of x. And then we also have the possibility that sine of x minus 1 is equal to 0. So cosine of x is equal to 0. Well, what are those solutions going to look like? Well, that means we're looking for angles where there's an x coordinate of 0. So that will happen at an angle of pi over 2. So that is the point where we have 0, 1. And then it would also happen at an angle of 3 pi over 2. So 3 pi over 2 would also work because that also has cosine equal to 0. And so we get two solutions from this part. One is x is equal to pi over 2, and one is equal to 3 pi over 2. X is equal to 3 pi over 2. So what about this other part? Well, if we solve this one, we get sine of x is equal to 1. So at what angle is that going to happen? Well, that's also going to happen at pi over 2. Right? If you go to an angle of pi over 2, that is the only place on the unit circle where the y coordinate is equal to 1. And so we also get this solution, x is equal to pi over 2 here. And so really you don't need to write it down twice, right? There's nothing wrong with getting the solution here again, but basically it's redundant. So if you were asked to kind of find all solutions, you wouldn't list it twice. You would just list it once. It's kind of like in 141 with multiplicity, right? We're getting the same answer twice. Doesn't mean there's anything wrong with the answer, but we don't really need to list it both times. All right, let's look at this graph. So when I graph this, instead of graphing the original equation, I'm going to graph this. So y is equal to sine of x times cosine of x minus cosine of x, so that we can see where is that equation, where is that function equal to 0. So that is this one. So again, got some interesting waves going on here. So we can see that we get a solution at pi over 2 and 3 pi over 2. And those are the only two places where this function equals 0, between 0 and 2 pi. All right, so last thing we're going to do is going to be a little different because we're now going to be looking at equations that do not just involve sine and cosine. So these are equations that I decided to include in this video because they are going to come up a lot again in calculus. In calculus, there's going to be a lot of times where you're working with functions that kind of blend together, polynomials and exponential functions and trigonometric functions. You have like different types of functions blended together. And so it's really important to know basically that you can do the same stuff that you do with more simple equations with these more complicated equations. So we're going to, for the first example, find all solutions to e to the x times sine of x plus e to the x is equal to 0. And again, we're going to be focusing on the interval from 0 to 2 pi. Okay, so this is going to be actually very, very similar to the examples that we were doing on the previous page. The only difference is that now instead of just dealing with sine of x and cosine of x, we have e to the x. But in terms of how the factoring goes, it's very, very similar. Because if we look at these two things here, what do they have in common? They both have a common factor of e to the x. So we can start by factoring out e to the x. So if we factor out e to the x, we're left with sine of x plus 1. So from here, what do we do? Well, it's the same as in all the other examples. So solving by factoring, if you have two things multiplied equal to 0, that means one of those things has to be 0. So our options are that e to the x is equal to 0, or that sine of x plus 1 is equal to 0. So let's start with the first one. So e to the x is equal to 0. So this is a really kind of handy fact to be aware of. And actually, before I say it, I would encourage you to maybe pause the video and try to think how you would solve this, and try to think if you can come up with a number x that works. If you can just, by looking at it, by experimenting with numbers, see if you can find a number x that you can raise e to and get 0. So try as hard as you can, but you're never, ever, ever going to find a number that will work. So remember, what is e? E is a number, right? E is a number. It's approximately equal to 2.72. So if you take a number, a positive number, and you raise it to a power, there's just no way that you're ever going to get 0. And so this part of the equation actually has no solution. And again, that doesn't mean that the whole equation has no solution. It just means that this part is not going to be the part that's going to make your answer 0, right? If you have two things multiplied together, it's not that both of them have to be 0, just one of them has to be 0. And so basically this tells us, okay, this is not going to be the part that equals 0. So this is, again, a really handy fact to know, and this will definitely come up in Calculus 1, knowing that if you're trying to solve an exponential equal to 0, there's no solution. There's no number x that works. You might guess x equals 0 would work, but what is any number raised to the 0 power? It's actually 1. So nothing's going to work. There's no solution. On the other hand, this part, the second part, we can solve. So this would be sine of x is equal to -1. And so where is that going to happen? That's going to happen at an angle of 3 pi over 2, because that's the angle the only angle between 0 and 2 pi where we have a y coordinate of -1. So from this part, we get x is equal to 3 pi over 2, and so that's our only solution to this equation. So let's take a look at this graph. So y is equal to e to the x times sine of x plus e to the x. So this one's a little crazy. It has waves to it, but also notice it gets like, I probably can't even scroll. So if you remember what exponential functions look like, they grow and grow and grow and grow. And so basically because of that, this function is just getting bigger and bigger and bigger and bigger as you go to the right. But if we focus on looking at where is it equal to 0, well, we see that the only place between 0 and 2 pi where this function equals 0 is at 3 pi over 2. Okay, so last one. So last example is now going to be blending together polynomial with a trig function. So we're going to find all solutions to x squared times cosine of x minus 9 times cosine of x is equal to 0. Oh, on the interval. You're probably sick of me rewriting this every time, but that's okay. I'm sick of it too. Okay. So again, just like the last one, we want to look for common factors. We want to look for what do these two things have in common? What can we factor out from both of them? So we have x squared times cosine of x minus 9 times cosine of x is equal to 0. So what can we factor out from both of these? Cosine of x. So if we factor out cosine of x, we're left with x squared minus 9. So x squared minus 9 can actually be factored even further, right? X squared minus 9 is a difference of squares. So we can keep factoring this by writing cosine of x times x plus 3 times x minus 3 is equal to 0. So now we have three things being multiplied together equaling 0, and so that tells us one of them has to be 0. So our options are cosine of x is equal to 0, x plus 3 is equal to 0, or x minus 3 is equal to 0. So let's start with cosine of x is equal to 0. So that's going to happen when we have an x coordinate of 0. So we've seen that one actually already today. So that's going to happen at an angle of pi over 2. And it's also going to happen at an angle of 3 pi over 2. So the two solutions that come from this part are x is equal to pi over 2 and x is equal to 3 pi over 2. Okay, so what about this next part? Well, this we just solved normally. So we get x is equal to -3. However, notice that because of how I wrote this question, I said to find all solutions on a specific interval. So this number actually isn't in that interval. So we wouldn't include this solution if you're asked for solutions between 0 and 2 pi, right? Because even though when we write something down like from 0 to 2 pi, we're usually thinking of angles, numbers fit into that as well. And -3 is a negative number, so it's not between 0 and 2 pi. So this is not between 0 and 2 pi, so we can get rid of it. But this other one, if we solve it, so if we solve x minus 3 is equal to 0, that's going to give us x is equal to +3. And that is between 0 and 2 pi, right? Because 2 pi is approximately 6.28, so 3 is between 0 and 2 pi. So our final answer is, and maybe I should have done this on the other ones, I want to make it clear that basically everything you get is part of the solution, right? These are all solutions. So if this was on the homework, you would want to type in like everything you got from every like separate part. Even though we're kind of solving them as separate equations, together they're all the different solutions to the original equation. So last graph, let's just take a peek at this one. So y is equal to x squared times cosine of x minus 9 times cosine of x. So again, kind of interesting. We see like it has some waves to it, but this one, just like the last one, really kind of grows out of control as you go further right. So you can see like a peak here, but we can't even, you'd have to scroll up a lot to see more of it. So if we're looking just between 0 and 2 pi for where it crosses the x-axis, we see pi over 2, which we found. We see 3 pi over 2, which we found, and we see 3. And then we can also see that there's another solution over here at -3, which we didn't include because of where we were looking for solutions, but that is another solution. All right, so that is it for today. And yeah, tomorrow we're going to be doing our last video about solving trigonometric equations. And like I said, then we'll be moving on to some other new stuff. I will see you then.